Okay, so this is continuing our discussion in Chapter 8 related to losses in pipe flow. So I'm trying to write on a surface here, so hopefully this turns out okay. I maybe will go a little faster in this video than I normally would in my notes. So of course, when you're watching this on your own, feel free to stop and pause and rewind if you need to. So what we're going to talk about in this section are what are called minor losses. And minor losses are a type of loss that are different than maybe the regular losses that we've already talked about, say the Moody diagrams, what's in the Moody diagram. And these are losses that can be due to, again, head losses, due to things like expansions in pipes, or also similarly contractions in pipes. You can also have things even like bends and elbows in pipes. And also things even like valves, like a ball valve or a check valve. Or also even things at like entrances and exits of pipes. Spelled that wrong. Right, so this distinguishes these from what are called major losses, which is what we talked about on Tuesday, and these are the losses that are due to what we talked about with the Moody diagram. The flow due to minor losses is typically very complicated. So things like flows in pipes and bends and expansions and contractions. So we'll try to show some examples. Flow due to minor losses is very complicated, so it makes it difficult to analyze. However, it can be easily quantified. And so for minor losses, which is generally we know H sub m, so H being the head loss, the minor head loss, we know that this is proportional to V squared over 2G. And of course we throw a K in there to make it an equality. So it becomes H sub m is equal to K times V bar squared over 2G. And where K is what's called a loss coefficient. And it is a dimensionless constant. And of course, if you convert back in terms of pressure drop rather than in terms of loss, this just ends up being that delta P, the pressure drop across, is equal to 1/2 K rho V bar squared. Now, since K is dimensionless, of course that means the hint is that it's going to lead to dimensional analysis. Usually you have to find it through some sort of experiment. Maybe you can do it through some simple, in some simple cases you can get a solution from Navier-Stokes, or you can do a computation. But generally it's going to be a function of the Reynolds number, and it's also a function of the geometry. Now, generally, the Reynolds number dependence is not that strong. So for the purposes of this class, we're not going to say that the Reynolds number dependence is not important. So really, we're just going to say that K is just a function of the geometry. And so now your total losses, so I'll write this as H subtotal for your system, is going to be H sub F plus sum of H sub M, again, where H sub F is your major losses, and then the sum meaning that it's the sum of all the minor losses. So we'll do a couple of examples. So for example, let's talk about flow in a pipe inlet. And it's where the flow is not fully developed. So if we have our pipe here, you have flow starting to come in this way. If you actually plot now, if I were to plot, oops, the pressure here as a function of the distance, try to use some different colors here, it's going to kind of look like well, try that as best as I can. Try that again. Where the pressure is actually going to be linear in this region, so linear with respect to x, but then it's not linear near the entrance of the tube. So I'll say this is a linear portion here. And there is actually going to be now some additional pressure loss. So this linear part, right, this would be the losses predicted by Moody. And then there's actually going to be even some additional loss at the front here. So in other words, if you take the linear part and extrapolate it out towards the front, as I've done over here, there's some additional delta P. And then knowing this delta P, you can just say your loss coefficient is going to be the delta P divided by 1/2 rho V bar squared if we were to do an experiment. Similarly, the Venturi we've talked about already. But if you have the flow through a contraction like the Venturi, again, if you plot the pressure as a function of the position, so the pressure decreases, then it partially recovers, right? But it doesn't fully recover. So in other words, this pressure here if we extrapolate that pressure over, there is going to be some finite change in pressure, and this delta P here, this would be related to the minor loss. Okay, so we're going to ask what causes this minor losses. Oops. Oh, I'm losing my letters here. Now the short answer is viscosity. I'll try to show an example as to why that is. So if you have pipe flow near the entrance of a pipe, so let's say it's a sharp-edged pipe, sometimes you can get what's called flow separation near the entrance, where you can get these small eddies here. So in other words, as the flow actually comes in, it actually detaches, and you get these little recirculation bubbles here on the corners. But now let's just say that we have some point 1 here and some point 2 here, and we know that the width of 2 has to be greater than the width at 1 because of the separation bubble, right? So that width is necessarily smaller than this width. But then we also know that by continuity, we know that since the width of 2 is smaller, that means velocity at 2, velocity at 1 has to be greater than the velocity at 2. Now, if it's inviscid, and we can use Bernoulli, then Bernoulli tells us because the speed is decreasing, we know that P of 1 has to be less than P at 2. Right. So as the speed is decreasing, but we actually know not all of this happens, meaning that the actual, so in other words, P2 by Bernoulli is always going to be greater than the pressure that you might see P2 in a real flow, or in other words, a viscous flow. So what that means is that there's some kinetic energy that cannot be reconverted into pressure work. and instead that energy is dissipated by viscous losses or by viscous effects. Now, if you round the edges, that can actually, rounded edges can reduce the flow separation and can actually therefore reduce the losses as opposed to a sharp edge. So we'll say the K, the loss coefficient, so for sharp-edged, sharp corners, I guess I should say sharp corners. Sharp cornered pipe, we'll say that is equal to about 0.5, and we'll just use that for this class. And we'll say there's no RE, Reynolds number dependence. Now, some other examples of losses, when you actually have the exit of flow, a pipe into a large reservoir. So in other words, if I have my flow just going into some large volume, in that case your loss coefficient is actually about equal to 1. And physically that means that the kinetic energy of the flow is all lost. So kinetic energy of the flow exiting the pipe is lost. So in other words, as it comes to rest. So there's kinetic energy, the flow is brought to a rest, and that's actually an irreversible dissipation. And just following up more, some other examples, sort of want to touch on this already, but in the Venturi, if your flow in the downstream end of the Venturi so you have, if these are say streamlines, you can get like these separation bubbles here, especially right in the corner. As I said before, where the flow separates, so you get this like eddying and this mixing, these eddies here. So these are called separation zones or separation bubbles. So that's what these are. Right? So these separation zones just dissipate mechanical energy. Now it does depend, in this, for the Venturi, the K is strongly dependent on the geometry, and it depends on how quickly the Venturi expands. So in other words, an abrupt expansion tends to dissipate more energy, therefore it has a larger K, versus something that's smoothly varying or smoothly transitioning tends to not dissipate as much energy and therefore has a smaller loss coefficient. And then the last example, talk about a bend. So in other words, if I have flow in a bend, and if these are my streamlines, you can also get a separation bubble on this side. And again, this separation bubble here. So the loss coefficients so the loss coefficients are tabulated. So for example, in your book, figure 825 and 826 actually has it's actually a figure, but this is a figure for flow, the loss coefficients for expansions and contractions. For example, let's see, figure 829 has the loss coefficient for flow in a bend. And even things like table 8.2 actually has things like in elbows and various other pipe fittings. So, right, the nice thing about this loss coefficient is that, as I mentioned before, but I'll just reiterate, is that the flow inside of these things like elbows and bends, the flow is very complex, but it still is actually easy to quantify them in terms of losses. Easy to quantify effect. Oops. And again, and we just do that through the K, the loss coefficient. So we'll do a quick example of how to deal with minor losses. So the example is that we have two reservoirs at different heights. So let's just say I have this reservoir on the right is at a lower height than this reservoir on the left. And that's our free surfaces. So of course your flow is going to tend to go this way. And let's say you know this length. It's the length of this tube or this pipe. And let's say you also know what the velocity is in here. And also say the diameter of this pipe you also know. And what we're going to try to find is just an expression for the losses. So we know, right, the expression for the head loss is going to be, you have the total is equal to the major losses or the Moody losses plus whatever the sum of your minor losses. And in this case, we're going to have two minor losses, right? The inlet and the outlet. So we know from the Darcy-Weisbach equation, right, we know the major loss in this case is going to be due to the friction factor times L over D times V bar squared over 2G. And the minor losses are going to be, we're going to have one at the inlet. And we're just going to say that's Ki for the K of the inlet. And that's going to be times V squared over 2G. And then we're going to have one for the outlet. And we're going to say that's K sub O times V bar squared over 2G. And now, as I mentioned before, you can say that Ki, the inlet, is about 1/2, and the outlet, Ko, is about 1. So again, since it's a larger reservoir. So then my total loss is the major loss component. And I'm going to write this, simplify it as Ko plus Ki V bar squared over 2G. Those are my minor loss components. Now notice there's a common factor of V squared over 2G in all of these. So we can simplify it and just say that the total loss then is still going to be V squared over 2G times the quantity of F L over D plus Ko plus Ki. So this is our final answer. Now, of course, we can substitute in what the 1/2, the value of 1/2 for the inlet and the value of 1 for the outlet, but it's not necessary here. Okay, so there's two additional topics, one of which I'll cover briefly, which is flow in non-circular ducts. You have one homework problem on this. We actually use a parameter that's called the hydraulic diameter. And we use the symbol D sub H. This is useful to characterize losses in non-circular ducts. So what the hydraulic diameter is We'll do some examples here, but it's 4 times the cross-sectional area divided by the perimeter. And now, once you have DH, or excuse me, once you know the hydraulic diameter, you can still write the losses as using the Darcy-Weisbach equation. You write V squared over 2G, but then you write times L, and instead of using the diameter, you use DH. So we'll go through a couple of examples of how to calculate a hydraulic diameter. So for a circle, okay, that's kind of the easiest example. This is part of the reason where that formula comes from. So it's 4 times the cross-sectional area. Well, cross-sectional area is pi over 4 d squared divided by the perimeter. Well, again, remember the perimeter of a circle is the same as the circumference, so it's just pi times d. So lo and behold, you just get d. So the hydraulic diameter is a diameter. Now for a rectangle, and let's say this is a rectangle that has side A and B. Your DH, again, 4 times the area, the cross-sectional area, which is just going to be A times B, divided by the perimeter. Well, the perimeter is going to be, just counting up the lengths of each sides, is 2A plus 2B, right? So that's this length, this length, this length, and that length. So then your DH you can simplify then as just twice A times B divided by A plus B. Now notice for the square, if it's a square, right, that's just the rectangle, but A is equal to B. Then you just get that DH is just equal to A. So that's easy. Do one more example. If you have the equilateral triangle, and let's say at its side, each side has length A. And if you remember, if you write the area of an equilateral triangle in terms of its side, it's root 3 over 4 times A squared, and that's the area, divided by the perimeter, which is just 3 times A. So in other words, it's going to simplify and you get that DH is equal to root 3 times A. Okay, so then the last piece of information that we need is that when you have a fully developed laminar flow, this is for flow in non-circular ducts, you usually get a relationship that F, the friction factor, is just equal to some constant divided by what's called REH, where REH is the Reynolds number, but based on the hydraulic diameter. and this constant C is going to be dependent on the geometry. I don't think we're going to do turbulent flows in non-circular ducts, but let's just do as an example. So if it's a square, so a square-shaped channel, this constant is equal to about 56.9, just for example. Lastly, we're not going to really do turbulent flows in non-circular ducts, but just for a little context. You can actually still use the Moody diagram, but of course replacing, again, making the substitution that you're using the Reynolds number based on the hydraulic diameter. So you can still use the Moody diagram to get your friction factor as a function of your hydraulic Reynolds number, and then of course the relative roughness. Now this is rather kind of a crude approach. It's only accurate to maybe 20% or 25%. But if you don't have any other information to go on, it's not too bad. So just as example, for the laminar flows, table 8.3 in the book has the C's for example, flow in a square channel, and also for flow like in a annular tube. So that's it. Now I'll say that there's one more section that's in the notes that's on a little bit more about pumps, but I think that's an important section, so I'm not going to cover that until the following Tuesday, and we're not going to cover it in this flip video. So thanks for listening. Losses